Hello, this is Dr. Brown. In this video, we're going to cover the information you'll need to do well on test 3. To start off with, we're going to consider some concepts you'll need to be able to understand and work on the test. You need to be able to calculate critical points of a functions. The critical point is where the first derivative is equal to 0, or either the first derivative is not defined. Here you'll see 5 points that are critical. You'll see 3 points where the tangent line has a 0 slope, so the derivative is 0. And you'll also see 2 points where the derivative is not defined, where there's a sharp point there, and you cannot calculate the slope of the tangent line. You'll also need to be able to determine for a function y equal f of x, determine intervals in which the function is increasing. That's when the first derivative is more than 0, or it's decreasing, the first derivative is less than 0. So you see in this particular function, we have an area here where the slope of the tangent line is positive. So it's an increasing function. Here in the middle, the slope of the tangent line anywhere would be less than 0. And so it's decreasing. And then to the right here, the derivative is more than 0, so it is increasing. Now, looking at a function, you'll need to be able to calculate what we call the absolute max or the absolute minimum value of the function, or in some cases, the relative max or the relative min of a function. Now, you need to remember that if a function is defined over a closed interval between a and b, you must also evaluate the function at the endpoints as well as the critical points. So this particular function you see here is defined between a, in this particular case, between a and e. And so you see, for instance, here a relative max, relative min. This point would be the absolute max, and this point would be a relative min. And the endpoint, and you need to look at the endpoints. In this particular case, this endpoint is absolute minimum. And point E here would be a relative minimum. In other words, it's the smallest in this area. You'll also need to be able to understand the mean value theorem, which says that if you have a function that it can be differentiated between a and b, and here's the function right here, and if it's differentiable on continuous on a and b, there has to be a point C somewhere between a and b such that the derivative at that point C is equal to the slope of the line between point A and point B of the function. In other words, the slope of this particular line here is f of b minus f of a divided by b minus a. That's just simply the slope of the line. It says that if all these conditions are met, that there's got to be at least one point where the slope of the tangent line is equal to the slope of the secant line between A and B. And here in this example, you'll see point C1, where the slope of the tangent line, if you drew it, would be parallel to the secant line. In this particular case, there is another point down here, C2, where the slope of the tangent line is parallel to the secant line. So usually you'll be able to find one or two like that. Sometimes, for instance, if you had a function that looked like this, I'm not drawing it very well, but here is the slope of the secant line. And you can see there's a point, say, right here, where the tangent line is parallel, maybe right here, maybe right here, maybe right here, maybe right here, and maybe right here. We also need to understand the concept of a function having points where the curve is concave up or concave down. If it's concave up, it looks like this. If it's concave down, it looks like this. So look at this particular function here. You can see that it is up here. It is down here. And it is up here. And then it goes down. Then it's up. And there are points between the regions where it's up and down called inflection points. And at these particular points, the second derivative will be 0. Now, if it's concave up, the second derivative is more than 0. If it's concave down, the second derivative is less than 0. So this can help you tell whether you have a relative min or a relative max by finding the critical points where the derivative is 0, and then check the second derivative. If f double prime is more than 0, it's concave up, so it's a relative min. If f double prime is less than 0, it's concave down and it's a relative max. And we will illustrate that in some of the problems that we work. Another thing you'll need to do is use L'Hopital's rule to find limits. You may have to rewrite the problem so that if you plug in the numerator and denominator, you get 0 over 0 or infinity over infinity. And we'll illustrate L'Hopital's rule in just a minute. You need to be able to solve a max or a min application problems. You need to be able to calculate antiderivatives. In other words, if f prime, it's f lowercase f of t is a function, its antiderivative would be given as capital F of t, and it just simply means that the derivative of f of t, capital F of t, is equal to little f of t. You need to also be able to solve initial value problems where you're given the first derivative or second derivative or the position s or the position double prime and determine y or s as required. You'll solve by finding the antiderivative, adding a constant each time you integrate, and solve for the constants by using the initial values or values given at a point. Now, getting into some problems, some of them you can just look at and get the answer just visually. Here you want to find the maximum extremum of this function that you're given here. Notice it's not a continuous function, but just looking at it, you'll see at this point is the absolute maximum that occurs at x equal minus 1. I would also notice that this point at x equal 1, it's a relative max. And this point, if you'd been asked, is an absolute min. And this point is a relative min. Now here we want to find the absolute extremum of the function on the interval minus 3 to plus 5. And remember, you need to check the endpoints and also the critical points. So the first thing we'll do is look at the critical points. And g prime is equal to minus 12x. And you set it equal to 0, and that means that x equals 0 is critical point. So now we calculate the value of the function at the critical point, and that's plugging in, you get 10 minus 6, 0 squared equal to 10. So this is a value at the critical point, and now we need to check the left endpoint. And that would be g at minus 3, which is equal to 10 minus 6 minus 3 squared equal minus 44. And then we'll calculate the function at the other endpoint, which is going to be at x equal 5, which is 10 minus 6 times 5 squared, and you calculate that, and that's equal minus 140. So looking at the three values we have, this is the absolute max, and this is the absolute min. So the answer is C here. Absolute maximum is 10 at x equals 0, and the minimum absolute is minus 140 at x equals 5. Okay, in this particular function, we want to just find all the critical points for the function. So calculate the first derivative. It's 240 x squared minus 15 x to the fourth. And set that equal to 0. And we can factor 15x squared out and leave 16 minus x squared equal to 0. You can further factor that into 15x squared times 4 minus x, 4 plus x. Set that equal to 0, and you see the critical points are x equals 0, x equals 4, and x equals minus 4. And that's answer D here. Now we got the mean value theorem, and we have a function, a quadratic function, that is definitely differentiable between 2 and 3. And so we want to calculate alpha b minus alpha of a divided by b minus a. A is 2, b is 3. Alpha of 3, if you plug it in, you get 3. Three squared plus 5 times 3 plus 4 equal 28 if you add it all up. Alpha of 2 is 2 squared plus 5 times 2 plus 4 equal to 18. And b minus a, of course, is equal to 1. So alpha of 3 minus alpha of 2 over b minus a, which is 1, is equal to 28 minus 18 divided by 1 equal 10. So now we need to calculate the first derivative and find out where it's equal to 10. So the first derivative is equal to 2x plus 5 equal to 10. And we solve and we get 2x equal 5. So x is equal to 5/2. So the value of c would be 5/2. Now, this particular function, we want to find the function's local and absolute extreme values, if any, and saying where they occur. Now, this is a cubic polynomial, and it will not have an absolute max or an absolute min because it will go to plus and minus infinity. So we're going to be looking for just local maximum, local minimum. So let's take the first derivative. The first derivative is equal to minus 3x squared plus 15x minus 18. And we set that equal to 0. And let's factor a minus 3 out, and we'll get x squared minus 5x plus 6. Set that equal to 0. And then we get factor the quadratic, and we get x minus 2 times x minus 3 equals 0. So x equal 2 and x equal 3 could be either local minimum or local maximum. And what we're going to do here, and one of the things you could do is graph this and pick out which is the local min or local max. Here I'm going to show you how you can take the second derivative, which is equal to minus 6x plus 15. And we're going to test second derivative at 2. And it's going to be minus 12 plus 15 equal 3. So that's more than 0, so it's concave up. So that means it's a relative or local min. Now looking at x equal 3, we get minus 18 plus 15 equal minus 3. That's less than 0. That means it's concave down. And I always draw a little upside down parabola, which means that it's a relative or a local max. And that answer is answer C. And you can also graph this and see that it'll have a maximum at 2 and a minimum at 3. And looks something like this. You can graph it too. I urge you to do that just to check your work. Now the next problem is going to be just a little bit involved. And we're not going to take the second derivative here. We're just going to take the first derivative to find the possible local maximum or minimum. And I have already graphed the function over here, which you can do on your calculator. And I urge you to do that just to check your work. So let's look at this function. The first derivative we'll use the quotient rule, which says you take the bottom, which is x squared plus 3x plus 5 times the derivative of the top, which is 1, minus the top times the derivative of the bottom. Now we're going to take the derivative of the bottom, which is 2x plus 3. And it's going to be divided by the denominator squared, which is x squared plus 3x plus 5 squared. Now we need to simplify this. H prime of x is equal to x squared plus 3x plus 5 minus, we'll have to FOIL this out, and we will get 2x squared plus x minus 3, all divided by the denominator squared. And you will see that this is equal to minus x squared plus 2x plus 8 divided again by the denominator squared. And I'm going to factor a minus 1 out of that and give you minus x squared minus 2x minus 8 divided by the denominator squared. It takes time to write this down. And now I'm going to factor the numerator into x minus 4 and x plus 2 divided by the denominator squared again. And we set that equal to 0 The only way it can be 0 is for x to be minus 2 or plus 4. Notice that the denominator squared is always positive, so we can determine whether the function is increasing or decreasing by looking at the sign of the numerator. So now we're going to figure out which one is relative min or relative max, and we're going to divide the x-axis into x more than minus infinity, less than minus 2, x more than minus 2, and 4, and then finally x between infinity and plus 4. And we want to test the numerator, and the numerator, I'm just going to write it down, is minus x minus 4 times x plus 2. And we'll have a test point for each of the intervals and pick an easy one. I would pick for this interval minus 3. For this interval, I would pick 0, seems to be the easiest one. And between 4 and infinity, I would just pick 5. So the sign or the numerator, we'll write down what it is. For x equal minus 3 would be minus 1 times minus 7 times minus 1 is less than 0. That means it is decreasing. We'll plug in 0 in the numerator and we get minus 1, minus 4, and 2, which is more than 0, which means it's increasing. And then we'll plug in 5 and we'll get minus 1 times 1 times 7, which is less than 0, so it's decreasing. So we can see that at the point minus 2, it goes from decreasing to increasing and then goes decreasing. So at x equal minus 2, it's a local min. And at x equal 4, it's a local max. And here is a graph. You see it's decreasing, increasing, and then just to the right of plus 4, it's decreasing again. So it's answer D, local minimum at minus 2, local maximum at 4. Here we have a combined logarithm and trig function, and we want to find the absolute maximum and minimum on the interval pi over 6 to 2 pi over 3. So remember, we're going to have to look at endpoints and we're going to have to look at the critical points. The first derivative of f, using the chain rule, the derivative of ln of plain old x would be 1 over x. So we're going to write 1 over sine of x, where u is sine of x, and then multiply by the derivative of sine of x, which is cosine of x. And set this to 0. And this occurs on when cosine of x is 0. We can't let sine of x equal 0 because we can't make the denominator 0. So we need to look at values of x where the cosine is 0, and that would be at x equal pi over 2 if you look at your unit circle. And that is the only point in between pi over 6 and 2 pi over 3. So now let's calculate F at pi over 2 is equal to ln of sine of pi over 2. Sine of pi over 2 is 1, so it's ln of 1. ln of 1 is 0. So the value at the critical point is 0. And now we need to look at the value at the left endpoint, which is pi over 6. So this would be ln sine of pi over 2. I'm sorry, pi over 6. Pi over sine of pi over 6 is 1/2. So that is equal to minus ln of 2. You might remember that ln of a over b is ln of a minus ln of b. That's from college algebra. This is approximately minus 0.69 if you calculate on your calculator. F of the right endpoint, f of 2 pi over 3, is equal to ln of sine of 2 pi over 3 is equal to ln sine of 2 pi over 3 is the square root of 3 over 2. And that's approximately equal to minus 0.14. So now looking at all these numbers, 0 is the absolute max, and the absolute minimum is minus 0.69 occurring at pi over 6. So the minimum at pi over 6 and the maximum 0 at x equal pi over 2. Here we have a function that's has a lot of discontinuities, but it says find the open intervals on which the function is increasing and decreasing. Identify the function's local and absolute extreme values, if any, saying where they occur. So just looking at it, this left endpoint is the absolute max. It's decreasing between minus 5 and 3. It is increasing between minus 3 and 0. And now we can also pick out the absolute min at x equal 5. And between 2 and 3, it's decreasing. So looking at the possible answers, you'll see it's answer B, increasing minus 3 to 0, decreasing minus 5 to minus 3. Excuse me, the way I pointed it out wasn't quite right. It was increasing from minus 3 to 0 and minus 5 let's cut that out and do it right. So let's see if I can. Okay, in this problem, we have a very discontinuous function. We want to find the open intervals on which the function is increasing and decreasing, and identify local and absolute extreme values, if any, and say where they occur. Well, the first thing I see when you look at this graph, you see an absolute max. And you see an absolute min. So this occurs at x equal 5 and absolute max at x equal minus 5. We see decreasing between minus 5 and minus 3. We see it increasing from minus 3 to 0. And we see it decreasing from 2 to 5. So it looks like the answer here is going to be A, increasing minus 3 to 0, decreasing minus 5 to minus 3, and from 2 to 5. And we have the absolute max at minus 5 and 0, and the minimum at 5 and minus 4. Now we have a function where we want to locate the local extrema and identify the intervals where the function is concave up and concave down. Well, right away, looking at it, you can see it is down here, and it is up here, and it looks like there's an inflection point at this point at x equals 0. And this is a local max, and this will be a local min. So the local minimum is at x equals 3, and the local maximum is at x equals minus 3, and as concave up from 0 to infinity, and concave down from minus infinity to 0. Okay, in the next problem, we're going to use L'Hopital's rule to find the limit. And L'Hopital's rule says that if you're trying to find the limit of, say, f of t divided by g of t, as t approaches some value, and if you plug in and you get 0 over 0, or infinity over infinity, that the limit would equal the limit as t approaches c of the derivative of the top, or numerator, divided by the derivative of the denominator. Now here we have this function, and if you plug in minus 3, you'll see you'll get 0 over 0. I'll leave it to you to do that, but you definitely will. So you can use L'Hopital's rule. If that didn't happen, then you can't use L'Hopital's rule. So this would be the limit as t approaches minus 3 of the derivative of the numerator, which is 3t squared, minus 6, divided by the derivative of the denominator, which is 2t, minus 1. Plugging in, we get 21 divided by minus 7 equal minus 3. So the limit is minus 3. Here again, we want to use L'Hopital's rule to find the following limit. Sometimes you need to rewrite it. So we need to rewrite. If we don't have a numerator and denominator, we're looking for the limit as x approaches pi from the left of pi minus x divided by tangent of x. Remember, cotangent of x is equal to 1 over tangent of x. And now if you plug in, you get 0 over tangent of pi, which is 0 over 0. So we can use L'Hopital's rule. So this limit then will be the limit as x approaches pi from the left of the derivative of pi minus x, which is just simply minus 1. Derivative of pi is 0, and the derivative of tangent of x is secant squared of x. So now we're looking at the limit as x approaches pi from the left of minus 1 over, remember, secant squared is 1 over cosine squared of x. So that's equal to the limit as x approaches pi from the left. That's equal to minus cosine squared of x. So that's equal to minus cosine squared of pi. Cosine of pi is minus 1, so that's minus 1 squared, which is minus 1. So the limit is minus 1. Let's use L'Hopital's rule one more time. We have this function, and if you plug in x equals 0, we get 0 e to the 0 divided by e to the 0 minus 1. This is 0 over 1 minus 1 equals 0 over 0. So we can, because this is so, we can now use L'Hopital's rule. So now we need to take the derivative with respect to x of x e to the x. And we're going to do this separately here because we're going to have to use the product rule. So that's going to be the first times the derivative of the second. The derivative of the second is e to the x plus the second, which is e to the x, times the derivative of the first. Derivative of x is 1. So we get x e to the x plus e to the x. Now, the derivative of the numerator is just simply the derivative of e to the x, which is e to the x. Derivative minus 1 is 0. So now the limit as x approaches 0 of x e to the x over e to the x minus 1 is equal to the limit as x approaches 0 of this numerator, which is x e to the x plus e to the x, divided by the derivative of the numerator, which is e to the x. So now we're going to plug in x equals 0, and we get 0 plus e to the 0 over e to the 0. Of course, that's 1 over 1. So the limit is equal to 1. Now we're going to be doing some antiderivatives. In this particular problem, we're going to be taking the antiderivative of a power function. So the integral, or the antiderivative of x to the n dx, you'll remember, is x to the n plus 1 divided by n plus 1. So you'll have to, if it's x to the n, you'll have to increase the power by 1 and then divide by n plus 1. So the antiderivative of this, in fact, if say f is this, then the antiderivative capital F is going to be 7/5 x to the 6/5 plus 1 divided by 6/5 plus 1 is equal to 7/5 x to the 11/5 divided by 11/5. And you can see that that's equal to 7 divided by 11 times x to the 11/5. That's answer B. Now we've got a problem in which we want to calculate the maximum profit and find the number of units that must be produced. X is the number of units. The revenue is given as 6x, and the cost is given as C of x. And we want to maximize the profit. Well, the profit is equal to the revenue minus the cost. So P of x is equal to 6x minus the cost, which is 0.001 x squared plus 1.3x. plus 60. Simplifying this, we get P of x is equal to 4.7x minus 0.001x squared minus 60. 4.7 came from 6x minus 1.3x. So now we can take the first derivative is 4.7 minus 0.002x and set that equal to 0. And we get 0.002x equal 4.7, and x is equal to 4.7 divided by 0.002 equals 2,350 units that should be produced in order to maximize the profits. Now we want to find the most general antiderivative. If f is the function and f is the antiderivative, then f prime is equal to little f. So we want to take the antiderivative of this function, and notice we can always add a constant to it and it will still be, and it will then be what we call the most general derivative. Now what I would do is rewrite this as the integral x to the minus 7 minus e to the 4x plus secant squared of 2x dx. We rewrote it because we wanted to have the power function in the numerator. And now we use the power rule. That would be x to the minus 7 plus 1 over minus 7 plus 1. The antiderivative of e to the 4x is going to be e to the 4x divided by 4. You can look at your chart, but remember the derivative of e to the 4x is e to the 4x times 4. So we had to put a 4 in the numerator to take into account the power rule. The antiderivative of secant squared of 2x is tangent of 2x divided by 2. Here we're taking into account the power rule, and then we add a constant. So this is the answer. Now you may have a copy of the notes. It may have had rewritten this as plus, and then this would have been plus. But the way it's written here, there's a negative here. So I had to take that into account. You can correct your note. Now we want to find the most general antiderivative here. Here we need to rewrite this as the integral of t to the 1/2. Remember, the square root function is equal to t to the 1/2 power. And here we have a fourth root, so that would be minus t to the 1/4 dt. And now we just use the power rule antiderivative formula, and we get t to the 1/2 plus 1 over 1/2 plus 1 minus t to the 1/4 plus 1 divided by 1/4 plus 1 is equal to t to the 3/2 divided by 3/2 minus t to the 5/4. And this will be a plus a constant, by the way, divided by 5/4 plus a constant. And now divide by 3/2 and you get 2/3. T to the 3/2 minus t to the 5/4 times 4/5 plus a constant. And that is answer B. Now we have what we call an initial value problem. We're given that dr dt is this function, and we want to solve for r. And we'll do that by taking the antiderivative and using the initial value of r at minus pi equal minus 4 to solve for a constant. So r is going to be the antiderivative or the integral of 3t plus secant squared t dt. And that is going to be the antiderivative of 3t is 3t squared over 2. The antiderivative of tangent of secant squared is tangent t plus a constant. So r is given here. And we're given that r at minus pi, we're going to plug in minus pi, and we get 3 times minus pi squared over 2 plus tangent of minus pi plus a constant, and we're told that this is minus 4. Notice that tangent of minus pi is 0, so we get 3 pi squared over 2 plus c equal minus 4. So c is equal to minus 4 minus 3 pi squared over 2, solving for c. So now if that is c, we can go back to our formula and plug in what c is. And so r is equal to 3t squared over 2 plus tangent of t, and then add c is this, which is b minus 4 minus 3 pi squared over 2. And that is answer A. Now here we want to find the largest open interval where the function is changing as request. We want to look at where it's increasing. So in order to figure out where it's increasing or decreasing, we want to calculate the first derivative, which would be x over 2 minus 1/2. And we want to know when it's more than 0. And x over 2 is more than 1/2. So multiplying by 2, you get x is more than 1. So from 1 to infinity, it will be increasing. Which is the largest open interval where it would be increasing. Now, here we're given a very simple problem. We're given the derivative of a function, and we want to know the critical values. Well, critical values are where f prime of x equals 0. So we just simply set this equal to 0 and look at the factors we're already given. X equal 4 and x equal minus 2 are the critical values. Now here, it's just simply answering a few questions about the function, its derivative, and its second derivative. So for the function, let's look and see at points A, B, and C, whether it's negative or positive. Obviously at A, it's negative. At B, it's positive. At C, it's positive. Now, look at A and figure out what the derivative would be. Well, at A, the tangent line slope is positive, so it's positive. At B, it's also still positive. And at C, it's still positive. Now, let me erase it a little bit. And look at the second derivative. At A, it's concave up, so that the second derivative of f is more than 0, so it's positive. It looks to me like point B is an inflection point, which means it would be 0. And then at point C, we're concave down, which means the second derivative is negative. So that's the way to fill in this particular table. Now we have a function that we want to graph. And here I would just put this into your calculator. X squared minus 36 x plus 216. Be sure to use parentheses, divided by x minus 6. And to graph it, you want to set the window up just like it's shown here. Here it goes minus 30 to plus 30. So I've got minus 30 to plus 30. And then for y min, y max, minus 60 to plus 60. Then you graph it. And you get this. And it's pretty obvious. The answer is D. So we want to find the extreme values of this polynomial, where they occur. Once again, the polynomial it's not going to have an absolute max or min because it's going to go to infinity and minus infinity. but we can look for local min and local max. So let's calculate the first derivative. Is equal to 6x squared minus 18x minus 60. And I can factor this into 6 times x squared minus 3x minus 10 is equal to 6 times x minus 5 times x plus 2. Set that equal to 0, and we get x equal 5 and x equal minus 2. Now, these could be relative min or relative max, or we could call it local min or local max. To figure out which is which, for something as simple as this, where you can easily take the second derivative, I would take the second derivative and look at its value, and that would be 12x minus 18. So the second derivative at x equal 5 is equal to 60 minus 18 equal 42. That means it's concave up. So that means a local min. Now we plug in the second derivative at minus 2, and we get minus 24 minus 18 equal minus 42. That means it's concave down, a local max. So the answer is written down here. Plug in your minus 2 and plug in your 5, and you'll see the local max is 168. The local min at x equal 5 is minus 175. Now we want to find the absolute extreme values of the function on the interval. The function is 10 over x cubed between 0.1 and 1. So f of x is equal to 10 x to the minus 3. The first derivative then is minus 30 x to the minus 4. It's equal to minus 30 over x to the 4th. It is never equal to 0 because the numerator has to be 0 in order for it to be 0, and you certainly can't have the denominator equal to 0. So there is no critical point. Now let's look at the endpoints. Alpha at 1 is equal to 10 over 1 cubed, which is 10. And the left endpoint, alpha at 0.1, is equal to 10 over 0.1 cubed, equal 10,000. So the absolute max is 10,000. The absolute min is 10. Now we're going to do calculus related to the movement of an object in space. It's got a constant acceleration of minus 100 feet per second squared. The initial velocity is 1,000 feet per second, and its initial position is 100,000 feet. Now we're given that the acceleration, we want to find the equation for S of t then, which is the position of this body in space. We know that acceleration is equal to the second derivative of the position, and that is given as minus 100. Now to solve for S prime, we take the antiderivative. And of course, S prime is also the velocity. The antiderivative of minus 100 is minus 100t plus a constant. We'll call that C1. Now, V at 0 is given as 1,000. So V at 0, plug in here, would be minus 100 times 0 plus C1 equal 1,000. So C1 is equal to 1,000. So now we know the velocity, which is S prime, is equal to minus 100t plus 1,000. And now to get the position, we take the integral again, or take the antiderivative. The antiderivative of minus 100t is minus 50t squared. Antiderivative of 1,000 is 1,000t plus a constant. Now we're given that S at 0, plug that in, we get 0 plus C2 is supposed to be 100,000. So now we have all the information for the position of this object in space, and we can write down that S is equal to minus 50t squared plus 1,000t plus 100,000. Now in this problem, an object is dropped 9 feet above the surface of the moon, and we want to know how long it takes the object to hit the surface of the moon if the acceleration, which is the second derivative of S with respect to t, is equal to minus 5.2 feet per second squared. Notice that this is a lot smaller than the acceleration of an object that's dropped on the Earth. Of course, the Earth has a much greater mass. You probably can remember how the astronauts were hopping up and down on the moon very easily when they got there. So let's look at this. The second derivative of the position then is going to be minus 5.2. That means the velocity, which is equal to S prime, we could take the antiderivative of minus 5.2 and get minus 5.2 t plus C1. Now we're given that V of 0 equals 0. That means that C1 must equal 0. So we have V equal S prime equal minus 5.2 t. So S is going to be, the position is going to be the antiderivative of minus 5.2 t, which is minus 2.6 t squared plus C2. Now we know that S of 0, when it's dropped, its position is 9 feet above the moon surface. So S of 0 is equal to 9. So S of 0 is equal to minus 0 plus C2. So C2 equal 9. So S is minus 2.6 t squared plus 9. And we want to know how long will it take the object to hit the surface. Well, its surface, when it hits the surface, will be equal to 0. The position will be 0. So we need to solve minus 26 t squared equal minus 9 t squared. Excuse me, this is minus 2.6 t squared. So t squared is equal to minus 9 over minus 2.6. So t is equal to the square root of 9 over 2.6, which is 3 over the square root of 2.6, equals 1.861 seconds. So that's how long it took for the rock dropped above the surface of the moon from 9 feet takes to hit the surface. Now, pay careful attention to this problem. Okay, we're given the velocity of a moving body along the s-axis is given by ds dt is 9.8 t minus 5 from t equal 2 to t equals 7. And we want to find the body's displacement over the time intervals 2 to 7. And we're given that s equal s0 when t equals 0, although we're not given what s0 is. So if s prime is equal to 9.8 t minus 5, taking the antiderivative, we get s is equal to 4.9 t squared minus 5t plus a constant. Now we're said that s equal at 0 is equal to s sub 0. So s is equal to 4.9 t squared minus 5t plus s naught. Now we're not given s naught, the initial position, but we're asked to find the displacement. So when t is equal to 7, we get 4.9 times 7 squared minus 5 times 7 plus s0. And s at 2 is equal to 4.9 times 2 squared minus 2 times 10, 2 times 5, which is 10, plus s naught. So the displacement is equal to s of 7 minus s at 2. And we just need to subtract this from this. And so the displacement is equal to 4.9 7 squared minus 2 squared. Minus 25. Notice S naught minus S naught is 0. This is 35 minus 10, which is 25. And so multiplying that out, we get 195.5 is the displacement. And notice that we didn't have to know the initial position in order to get the displacement. The answer is 195.5. Now we have a problem relating to manufacturing again. It costs $14 to manufacture and distribute a backpack. If the backpacks sell at X dollars each, the number sold in is given by this formula. Find the selling price that will maximize profit. Now the profit is equal to the revenue minus the cost. Now the revenue we're selling in, and we're selling them for 14. We're selling in of them at X dollars each. So the revenue is going to be N times X. And the N that is sold, they cost $14 each. So the cost is 14 N. So the profit is equal to, I'm factoring an N out, is N times X minus 14. And we're given that N is this formula here. So we can say that the profit P is equal to 3 over X minus 14. I'm just going to plug N in to this formula. So this is N. We're going to multiply that times X minus 4, X plus X minus 14. And now when we do that, we will get 3 for 3 over X minus 14 times X minus 14 plus 6 times 100 minus X times X minus 14. Notice we got 6 times 100 minus X times X minus 14. And the profit is 3. We need to multiply this out, which is 6 times 100X minus 1400 minus X squared plus 14X. Just foiling that out. And this is going to be 3 plus 600X minus 8400. That's 6 times 14. Minus 6X squared plus 84X. And so simplifying this, we get the profit is equal to 684 X minus 8397 minus 6x squared. And now we take the first derivative of the profit and we get 684. The derivative of 8397 is 0 minus 12x equals 0. And we get x then is equal to 684 divided by 12 equal 57. So the selling price that will maximize the profit is $57. Now, the last problem here is a little bit involved. A storage shed is to be built in the shape of a box with a square base. Notice a square base. To have a volume of 170 cubic feet. And the concrete for the base costs $2 per square foot, and the material for the roof costs $4 per square foot, and the material for the sides costs $2.50 per square foot. Find the dimensions of the most economical shed. So let's calculate the area of the base. And we're going to have the area of each piece here, the area and the cost. And the base area is going to be x times x, which is x squared. And it costs $3 per square foot, so it's going to be costing at 3x squared. And then the roof is the same area, and it's going to cost $4 a square foot, so it'll be 4x squared. And then the walls, the area of one side of the wall is x times h, which is hx, and there are 4 walls, so there'll be 4hx would be the area, and they cost $2.50 per square foot, so 4 times 2.5 will be 10, so 10hx is the cost of the wall. So the total cost is 3x squared plus 4x squared plus 10hx, or 10xh. So we have a cost function C is equal to 7x squared plus 10xh. Now we got a function here that has 2 variables, x and h. How do we get it down to just x? We got to realize that the volume is going to be 175. So the volume of this is x times h. The volume then is x squared h. And that's supposed to be 175. So we can solve for h here is equal to 175 over x squared. And we can put this in this function, leading to c equals 7x squared plus 10xh equals 7x squared plus 10x times 175 over x squared. So now let's multiply all this out and we get C equals 7x squared. This is going to be 10 times 175, which is 1750. X into x squared goes x times. So we have the cost is 7x squared plus 1750 divided by x equals 7x squared plus 1750 x to the minus 1. Take the first derivatives to see if we can find the value of x that gives the dimensions of the most economical shed to minimize the cost. And so the derivative is 14x. Notice we rewrote 1750 over x to put x to the minus 1 in the numerator, and that's derivative is minus 1750 over x squared. And we set that equal to 0. And we get 14x equals 1750 over x squared. Cross multiply and you get 14x squared equals 1750. Cross multiply and you get 14x cubed equals 1750. And so x cubed equals 1750 over 14, which equals 125. So x is the cube root of 125, which is 5. So the length of one side of the shed's base is going to be 5 feet. The height we will get from the formula h equal 175 over x squared, which is 175 over 25 equals 7. So the height of the shed should be 7 feet. And that is the last of the problem.